Okay, section 14.3 is on integrated rate laws and half-lives. And if I have a reaction, say, that has A plus B going to some sort of products, remember I can define the rate law is equal to K, and let's suppose it's first order with respect to A and 0th order with respect to B. And then that rate is also equal to negative delta concentration of A over delta time. So these two are equal to each other. We can set them equal to each other and then do some rearrangements. We'll divide both sides by the concentration of A. And we'll multiply both sides by a delta T so that certain cancellations occur. And we're left with delta concentration of A over the concentration of A is equal to negative K delta T. And now what we've done here is we have gathered like terms on the same side. So all of our concentration of A terms are on the left, and then our other variable that we change, the delta T, is on the right. And if we take these deltas, these intervals, to get smaller and smaller and smaller, eventually we'll do a neat little trick invented by Leibniz and Newton, where we change them into infinitesimally small steps, and we'll represent with a dt and a d delta A. Well, now I can integrate both of these sides, right? If you've got dx, you can integrate with respect to the variable x. Here we're just going to integrate. These. And so on the left side, what is the integral of 1 over the concentration of A dA? That is going to be the natural log of the concentration of A. And that is going to equal negative K. And what's the integral of dt? That's just going to be T. And these will have to be evaluated over some interval. Okay, and this isn't meant to be a calculus class, so if you want, you can kind of just look at the solution here, and that's all you'll need to remember. But basically what this interval means is that I take the natural log of, let me erase up here. Now we've got that, so we'll write what is the full integrated rate law here. We'll take the natural log of A at time t minus the natural log of A at time 0, and that's going to equal negative K of t at time t minus a negative K times 0 when time is at time 0. And obviously this multiplying by 0 makes that second half go away. So this is the form of the integrated rate law. Oftentimes we'll move this over to the other side, so you'll have the natural log of A t is equal to a negative kt plus the natural log of A 0. And that's a constant, just your initial concentration, take its natural log, and so this is a constant. And when you write it like this, it actually becomes a linear form. And I know you're thinking this doesn't look like a line, there's natural logs everywhere, but if we let y equal the natural log of A And if we let x equal t, then this becomes y is equal to negative, and we'll say one more, we'll let m equal negative k, and we'll let b equal the natural log of a naught. Okay, well if we do all of that, I'll erase this form here. If we do all of that, natural log of a, well that's going to be y. And negative k, well that's m. T is x. And natural log of a is b. Y equals mx plus b is the form of a line. So as long as I have the natural log of a plotted against time, then I'm going to have what looks like a straight line. Hold on a second. I want to make sure I have it sloped in the right direction, and I do. Okay, it'll be negatively sloped because k is a positive value, and the slope is going to equal the negative of that positive value. So the slope is equal to negative k. That intercept is equal to the natural log of a naught. All right, so let me just show you real quick here what such a graph would look like. You know, if you're measuring the concentration several times a second with a electrochemical probe or a spectroscopic instrument, then you can construct these graphs easily, showing the concentration of A at every second through your instrument, and then you take it into a spreadsheet and just take the natural log of that concentration at every second, and that's what you plot. And we'll show you how to deal with spreadsheets at the end today, but I just wanted to sort of introduce this idea of how the first order integrated rate law it takes the form of a line. Okay, now we can also look at kind of some interesting points in the equation. So let's just have our integrated rate law right there. And let's say we're interested in how long it's going to take for the amount of reactant to drop to half of its initial value. So in other words, we want A of T, and this is going to be a special time. We'll call it T1 half. It's the time that's required for the concentration of A to drop to half of its initial value. A of T1 half is going to equal 1/2 of A naught. So let's plug those in here and we'll get a new sort of equation. So we'll have the natural log of 1/2 A naught is equal to negative K T1 half plus the natural log of A naught. Now we can combine these natural logs. If I have the natural log of 1/2 A naught minus the natural log of A naught equal to negative K times T1 half. Well, if I am subtracting two natural logs, this is just a bit of algebra when it comes to natural logs. I can, that's the same thing as taking their ratio. So this would be the natural log of 1/2 A naught divided by A naught, right, where this has come down into the denominator. It seems a little crazy, but that's how natural logs work. That's actually what makes natural logs really useful are properties like this. That's equal to negative k times t1/2. Okay, and these obviously cancel out, and so we get natural log of 1/2 is equal to negative k t1/2. Okay, and then another great property of logs is that I can flip the numerator and denominator here and just put a negative out in front instead. So in other words, I can write this 1/2 as 2 raised to the negative 1 power. Right, 1/2 is 2 raised to the negative first power, or the inverse of 2. And I can take this exponent and move it out here as a coefficient. And what we finally end up with is negative ln of 2 is equal to negative k t1/2. The negatives can go away, and the t1/2, the half-life, is going to equal the natural log of 2 over k, the rate constant. Okay, so one of the really interesting things about this is you'll notice that the half-life here is constant. The natural log of 2 is a value that is the same on everybody's calculator every day of the week. And then k, this rate constant, is going to be unique to a particular chemical reaction, but it remains constant throughout the course of the reaction. It doesn't matter whether your reactants are concentrated or dilute, whether you're at the beginning or near the end, k is the same. And so that means that your half-life is the same for first order kinetics. So let's look at kind of a figure that shows that. What we have is a beaker here with like a concentration of 0.8 molar. And we represent that with 8 little particles here in the beaker. Well, after a certain amount of time has passed, the concentration will drop to 0.4 molar. There's only 4 particles left in our figure. And that took some amount of time. We'll call that the half-life, t1/2. If we wanted to then wait until it drops to half of that value, so from 0.4 down to 0.2, it will take another period of time, and it is precisely the same length. So that half-life, it'll take precisely the same length of time to go from 4 to 2 as it had taken to go from 8 to 4. And then, of course, we can go from 0.2 molar to 0.1 molar, half again, and that will take the same period of time. It looks like the half-life here is 1 minute long, right? It takes 1 minute to go to half of the concentration. This is a property of first-order reactions that makes their half-lives really useful and convenient way. It makes the half-life be a very useful and convenient way to describe the future concentration of a substance. Okay, so let me get rid of that there. All right, so you can calculate the half-life in this way. And you could calculate, the concentration at some future time, but let's say not the half-life, just an arbitrary time. Let's say you wanted to know if I started with some initial concentration and I waited precisely 4.5 minutes, how much is left over? Well, you could certainly put the 4.5 minutes into your time, put in your initial concentration, and solve for the concentration at that time. But it's more convenient to use a half-life, and we'll show you how. Oops, I forgot this equation is not in your textbook. I don't have a figure for it, but it is convenient enough that I just looked it up, and I'll just give it to you now. So this is a bonus that's not in your textbook. And that is that the concentration of A at some future time is going to equal the initial concentration times 1/2 raised to the power of the number of half-lives. And that doesn't have to be an integer number. So let's suppose your half-life is 4.5 minutes. And let's suppose you're curious how much will be left after 10 minutes. And let's suppose that your initial concentration was 0.500 molar. Well, we can just plug those numbers in. Right, so my concentration of A at 10 minutes is going to equal 0.500 molar times 1/2 raised to the power. How many half-lives is that? Well, that would be 10 divided by 4.5, right? It's a little bit more than 2 half-lives, and we can just say 10 minutes divided by 4.5 minutes. That is going to be the number of half-lives. Okay, so let's put those numbers in a calculator and see what we get. Oops, sorry. There we go. So we're going to have 0.500 times 0.5 raised to the power of 10 divided by 4.5. And let's make a bit of a prediction here, right? So 10 minutes is a little bit over 2 half-lives. So the first half-life will go from 0.5 to 0.25. The second half-life will go from 0.25 to 0.125. So I'll expect to be just a little bit below that, maybe about 0.12. Let's see what we get. A little bit further than I thought, but 0.107 molar. I was within 10% with my quick estimation, 0.107. Okay, so that is the integrated rate law and the half-life. All of this, these great tools for predicting future concentrations and for quantifying the rate of decay in a convenient form, the half-life, come from the integrated rate law. Well, that was so successful. Why don't we try it with second order and 0th order kinetics as well. Okay, first order kinetics just means that your rate law was equal to K times the concentration of A, right? So second order kinetics would say that negative d concentration of A over dt is going to equal K concentration of A squared. So that's second order kinetics. Hold on a sec. Sorry, I wanted to adjust the camera ever so slightly because I keep just barely cutting off the top there. All right, so for second order kinetics, we'll do the same sort of trick. We'll move the like terms on the same side, so we end up with dA over A squared, and that is equal to negative K dt. And now we'll integrate both sides. Now, does anyone know the integral of 1 over x squared dx? It's going to be negative 1 over x, or negative 1 over the concentration of A, and that will be evaluated over an interval of 0 to t. And the integral here is still just the negative kt, and we will evaluate that over an interval from 0 to t. Let's see. So we can eliminate both of these negatives, and when we evaluate this over the interval, what we'll end up with is 1 over a of t minus 1 over a naught is going to equal kt minus k times 0. And again, we'll bring this constant over to the other side. So the second order integrated rate loss as 1 over at is equal to kt plus 1 over a naught. Now we can do the same trick here where we try to get a linear form. If I let 1 over at equal y, and k equal m, t equals x, and 1 over a naught is b, then we'll get an equation in a linear form. This time it'll be positively sloped. The slope will equal k if I plot 1 over the concentration of A versus time. And then we can get the half-life as well. The same way, we'll say that, at t is equal to t1/2. We know that A of t1/2 is equal to 1/2 the concentration of A naught. And so we'll plug that in. 1 over 1/2 A naught, the 2 will come up here. We'll have A naught, so 2 over A naught is equal to K t1/2 plus 1 over A naught. And we'll get these over onto the same side as each other. Well, let's just multiply everything by A naught to start with. Get rid of some problems there, so we'll end up with 2 is equal to A naught K t1/2 plus 1, and we'll subtract 1, so we get 1 is equal to A naught K t1/2, and so what is the half-life? Is equal to 1 over K times your initial concentration. That is a half-life for second-order kinetics. And this isn't nearly as convenient as the half-life for first-order kinetics because the initial concentration is a part of the equation. And so that means if I have a highly concentrated solution, then your half-life is going to be shorter because you'll be dividing by a large number. The half-life will be shorter for higher concentrated solutions, and the half-life will be longer for lower concentration solutions. And over the course of a reaction, your reactant's concentration will go down, and so that means that the half-life actually increases over the course of a reaction. There isn't one single half-life for second-order reactions, which makes it a lot less convenient, but still, I suppose, not entirely worth ignoring. Okay. And then if you wanted to figure out the concentration at some future time, you would just put your initial concentration in here and put whatever future time you're interested in, and then solve for AT. So we won't do a practice problem like that because I don't think it's as important, and I don't want to distract from the more important parts of this section. Oh boy, okay. How about for zeroth order kinetics? Here we're going to have the rate of negative d concentration of A over dt. That's going to equal just K. For zeroth order kinetics, it's just K. And so what we'll get is negative d concentration of A is equal to K dt. Integrate both of those, and you end up with negative concentration of A evaluated over an interval is going to equal KT evaluated over an interval. And so we get negative A of t minus a negative, so that'll be a plus A naught is equal to KT. And we'll go ahead and get A t on one side. We want AT to be a positive value, and so we'll invert everything. So that's going to equal a negative KT, and then this A naught will have been turned negative, and we'll do a positive to bring it over to the other side. A naught. So AT is equal to negative KT plus A naught. If you look at this, it's quite clear that we can just let the concentration of A equal Y. Negative K is equal to M, T is equal to X, and A naught is equal to B. So here if you have a graph of the concentration of A versus time, then it's going to look like this, and the slope is equal to negative K. And again, we can find a half-life, right? So 1/2 A naught is equal to negative K T1/2 plus A naught. So let's subtract the 1/2 A naught over here and add the negative, and add the K T1/2 over there. So we get K T1/2 is equal to 1/2 A naught. And finally, the T1/2 is going to equal A naught over 2K. And again, we've got a half-life that's defined in terms of the initial concentration. In this case, the half-life will get shorter and shorter as the reaction proceeds. The less reactant you have at any given point in time, the faster it will reach half of that amount. That makes sense because if this graph here is the concentration of A versus T, so in order to reach 1/2 of its initial value, this would be a half-life, and then in order to reach half of that value, this would be the half-life, and half of that value, this would be the half-life, and half of that value. And as you see, they get smaller and smaller and smaller. Eventually, you've got such a small concentration that it will reach half of that value in just an instant. So what we see from this is that you can tell the reaction order just by identifying which graph is going to be linear. The concentration of A, the natural log of A, or the inverse of A versus time. and we can use the slope of that line to tell what the rate constant will be. So let's look at one figure, and then we'll look at some data on an actual spreadsheet. Okay, so if you collected data and you graphed the concentration of A versus time, and it showed some curvature, that tells you that it is not a 0th order reaction. If you graph the natural log of A over time and there's still some curvature there, then that tells you that it is not a 1st order reaction. Then you graph 1 over A versus time, and now that is a perfectly straight line. That tells you, pardon me, that tells you it's a 2nd order reaction. And remember, for 2nd order reactions, the rate constant is equal to positive K. And so not only do we have a 2nd order reaction, but we can see here that the rate constant is 0.0023. Now, for a 2nd order reaction, the units of K would be inverse molar inverse second. So that's 0.0023 inverse molar inverse seconds. Okay, and give me a minute here. That's the one. Okay, now I've got a spreadsheet here, and I'll go ahead and make it fill the screen. Or, yeah, here. Now you can see my face while I work. Okay, so what I have is reaction A plus B goes to C. And we've got the time here, the concentration of A, the concentration of B, the concentration of C. And in reality, we don't need the concentration of C, but I just had included it in there for completeness' sake. Now, I'm going to take a graph of A versus T, and I'm going to insert a chart. And this process is a little bit different on Microsoft Excel. Here I'm using LibreOffice Calc, and I'll actually show you an example with Microsoft Excel when we look at quiz 14.2, so you can see it both ways. I use LibreOffice on my laptop just because it's a Linux laptop, and so I don't have Microsoft on there. Now, so I'm going to make a, oops, not a line, a scatter. I'm going to make a scatter chart, and I like to do the lines when you've got lots of data points. Having a bunch of dots isn't as helpful as just drawing a smooth line. So I'll go ahead and be sloppy with my axes and just hit finish instead of giving axis labels, because what we can see is that this is clearly curved. It's curved, so this is not a 0th order reaction. Okay, so we'll delete that. And let's figure out how it looks if I plot the natural log of A. So I'm going to hit equals, and then ln for natural log, opening parenthesis, and then I'll click on the cell for the concentration of A. Close parenthesis and hit enter. And then in this corner here, if I double click, then that's going to apply that same formula all the way down. You can see here if I select this cell that it's taking the natural log of the appropriate cell that's 2 positions over. So the easiest way to graph this is just to graph all of them. And I did that by holding down Shift and pressing over 3 times, then holding down both Shift and Control, and I just press down. That'll select them all. And I'll insert my chart, make it a scatter, we'll finish. And then what I'm going to do is just kind of delete all the others. I don't I don't want A itself. I don't want B itself. I don't want C itself. And I'm left here with the natural log of A. And it looks like it's got some curvature as well. So that means this is not a first order reaction. Pardon me. And so I'm going to do 1 over the concentration of A. So I'm going to say equals 1 divided by, and select here the A column. And we'll double click. And do the same thing. We'll insert all of our data series on a single chart, and then we'll just delete the ones that we don't want. That's just the quickest, easiest way to do it. Okay, and we'll get rid of natural log of A, get rid of A, B, and C, and all we have left now is 1 over A, and look at that, it looks very straight indeed. So this is a second order reaction. And if we insert a trend line and we show the equation on the chart, then we can see that y is equal to 0.1208 times x plus 6.7. That 0.1208 suggests that our rate constant is 0.1208. And if you cheat and look down here in the equations, you can see that it is 0.12. So that was accurate to, within about 1/10 of 1%. Okay, now this reaction is second order overall, but is it second order with respect to A and 0th order with respect to B? Is it second order with respect to B and 0th order with respect to A? Or is it first order with respect to each of them and second order overall? There's no way to tell based on this first trial where we have the concentration of A and the concentration of B equal to each other at the beginning. So let's come over here. I've got some new data. Here I've got the concentration of A to be less than 1/10 of the concentration of B. And what that means is that if we scroll down to the end here, even as the concentration of A is approaching 0, you'll notice the concentration of B went from 0.15 to 0.14. That means that the concentration of B remains pretty much constant over the course of the reaction. It's not technically precisely constant, but it's really close. And what that means is that if my rate is equal to K times the concentration of A times the concentration of B, but because B is in excess and, Okay, so the rate is equal to K times the concentration of A times the concentration of B, and B is in excess, so it doesn't change over the course of the reaction. That means we can sort of wrap B up into the value of the rate constant, and for this run at least, the rate is going to equal K prime, which is the true rate constant times, the concentration of B times A raised to, whatever exponent there is. And the B, again, because it doesn't change, doesn't matter if it's 0th, first, or second order with respect to B. If B is remaining constant over the course of the reaction, then it can be wrapped up into this K prime. And so what we're doing is isolating the kinetic effect of reactant A. So let's put that spreadsheet back up there and see how things are different. Here we'll graph A versus time, and we'll see, okay, we will see if it is a 0th order with respect to A. Okay, and you can see that there is curvature there, so it is not 0th order with respect to A. So let's do the natural log, the concentration of A. Equals the natural log, and we'll go point to the cell for A. Extend that equation down, and we'll graph this. Insert a chart, scatter chart with lines, finish. Okay, and we'll get rid of all the things we don't care about. We'll get rid of A. I feel like my laptop is struggling. Sorry, technical difficulties. Maybe I can just pause the recording until this gets taken. Okay, we're back. I had to restart the spreadsheet, but I think this worked. So we notice the natural log of A actually looks very nicely straight. We'll show that equation on the chart. And here K is supposed to equal the negative of the rate constant. And you know, that's a very different rate constant than what we have here. But if I take that rate constant, 0.01719, and I multiply it by the average value of B over the course of this reaction, which is about 0.145. Oh, hold up. Oh, I'm sorry, and I divide it by, that's why. And if I divide it by the average value of B, which is about 0.145, then you'll notice, you know, it's not perfect, but I get pretty darn close to the 0.12 rate constant that we were expecting. So that means that this is first order with respect to A. So you can probably guess what's going to happen with respect to B, but we've got the data here to double check. This time we have A in a high concentration and B in a low concentration. So over the course of this data set, A goes only from 0.15 down here to about 0.14. And we'll just skip to the chase. If we were to graph B over time, it would be curved. So let's graph the natural log of the concentration of B over time. And this time, I'm going to reference the concentration of B instead of A. And we'll insert the chart. And we see that that natural log of B does indeed look nice and straight. And we can add a trend line, show the equation on the chart. And you know, this trend line actually looks exactly like the one for A because our data are perfect mirrors of each other. So in the end, we get a rate law that says the rate is equal to K, which we know is 0.12 inverse molar inverse seconds, concentration of A, concentration of B. So it's first order with respect to A, first order with respect to B, second order overall. And for these two trials where we put one of the reactants to be in excess, what we observed is first order kinetics, even though this is a second order reaction. And so what we call that is pseudo first order. Pseudo first order kinetics is what we observe when we have, say, put reactant B in excess, and we observe that it's first order with respect to A, but technically that trial doesn't have any information about the reaction order with respect to B. Okay, this was a long section, so we'll stop here.